All right, welcome everybody. So let's continue exploring matrix subspaces and the connection between the dimensions of these subspaces and the matrix A itself. So let's imagine we have a matrix A which is m by n. So this means we have 1, 2, m different rows in this matrix, and this matrix consists of n columns. So just recall that the null space of matrix A we define as the set of all vectors x that are solutions to the homogeneous equation ax equals the 0 vector. And the column space of matrix A is equal to the space that is spanned by the n different column vectors of matrix A. And so the dimension of the column space, that is what we call the rank of matrix A. And the dimension of the null space, we call that the nullity of matrix A. And one observation that we've made is that the dimension of the null space of matrix A is going to equal the number of free variables, and the column space is going to equal the number of pivots. And both of these things, number of free variables and pivots, we can identify these by putting the matrix into reduced row echelon form. So let's summarize the connection between all of these ideas in what is called the rank theorem. So the dimensions of the column space and the null space of an m by n matrix A have to satisfy the equation that the rank of A plus the nullity of A equals the number of columns of A. And hopefully this makes sense, because either out of the columns in matrix A, when we put it in reduced row echelon form, there's only two possibilities. Either that column has a pivot, or that column doesn't have a pivot and it is a free variable. So adding up the number of pivot columns and the number of non-pivot columns is going to equal the total number of columns in matrix A. Okay, so let's see how we can apply this rank theorem to answer a couple of questions down below. So question 1 is saying, if we know that matrix A has 10 rows and 6 columns, and the dimension of its null space is 4, meaning we have 4 free variables, what is the rank of matrix A? And so just recall the rank of matrix A, that is defined as the dimension of the column space of matrix A, and that is going to be a subspace of the codomain of the matrix, which would equal the number of rows in the matrix. And our matrix A has 10 rows, so the column space of matrix A is going to be a subspace of R10. It can have dimension at most 10. And so here's one way that matrix A could shake out. So it has 10 rows and 6 columns. So maybe the first row has a pivot. And then we're told that the nullity of the matrix is 4, so we must have 4 free variables. Let's just say the second column is free, the third column is free, the fourth column is free, and the fifth column is free. And then that would leave the last, sixth, and final column to also have a pivot. So maybe the matrix looks something like this. And in this case, the rank of the matrix is going to equal the number of pivot columns. So the rank of matrix A in this case would equal 2. And that means, yes, we have a subspace of the codomain, which was R10. The column space is a 2-dimensional subspace of the codomain. So let's consider the next example. So now we're going to switch the number of rows in columns. So let's let matrix A be a 6 by 10 matrix. We have 6 rows and 10 columns in this matrix. And we know that the nullity of this matrix is 3. So out of the 10 columns in this matrix, we know that 3 of them are free. And we want to figure out, well, what is the rank of matrix A? And so you might be thinking, well, let's just use this rank theorem above, which says, I don't know what the rank is. That's what we're being asked. But I do know the nullity is 3. And we have 10 columns. So according to this formula, we're going to say that the rank of A is equal to 7. However, recall that the column space of a matrix is going to be a subspace of the codomain. And the dimensions of the codomain are going to equal the number of rows in matrix A. So in this case, whatever the rank of matrix A is, since the column space is a subspace of the codomain, which has dimension 6, the rank of matrix A cannot be bigger than 6. So over here, according to this equation, we're saying that the rank of matrix A is 7, but this is impossible because the rank of matrix in this case would be at most 6. So therefore, there is no such matrix A 6 by 10 that has nullity 3. That would be impossible.